Good day to everyone. Thank you very much to everyone who is joining this webinar. My name is Anas. I am from Cybernet Systems Malaysia and has been working here as an application engineer, specializing in mechanical business units and also the fluid business unit. So today's presentation or today's webinar is going to be about the introduction to Ansys CFD. So Ansys CFD has been used for years now in recent time, especially when it comes to solving a complex problems that involve any kind of fluid flows or thermal fluid flows. So today we are going to go through what is Ansys CFD, what Ansys can offer when it comes to CFD analysis. So yeah, please sit tight and enjoy this presentation. So before that, I would like to ask the attendees today to please keep yourself muted throughout the presentation. And if you have any questions at any point of this presentation, please write your questions down in the chat box and I will try to answer all of your questions at the end of this webinar. So thank you for your cooperation. So now let's get through the agenda for today's. First, we will go through the introduction of Cybernet systems. And then we are going to continue with the overview of Ansys solution. And then we are going to go through the Ansys workbench. What is Ansys workbench? And then we are going to talk about a little bit just the general understanding of the Ansys CFD. And then next we are going to go to the Ansys Fluent. Ansys Fluent, like I mentioned briefly previously, is the product offered by Ansys for CFD analysis. So we are going to go through the overview of the Fluents, and then we are going to see the features and also type of analysis available in Ansys Fluent. We are going to see a application example, and then I'm just going to walk you through some other features on top of what already available inside the Ansys Fluent, such as the parallel computing capabilities, and also the Fluent mesh as well. Then afterwards, I will give a bit of demonstrations in this particular case regarding the internal flow of an exhaust system, just to give you some insight of what to expect when you are actually using this Ansys Fluent yourself. And then at the end of this presentation, we are open for the Q&A session. So first, we are going to start with the introduction to Cybernet systems. So Cybernet Systems has been around for almost 30 years now. Cybernet System HQ is located in Japan. So we are the Japan's largest CAE software distributor, Tier 1 listed company, and R&D and also sales subsidiary all over the world. So out of Japan, we have 4 overseas sales subsidiary, namely the Cybernet Taiwan, Cybernet China, Cybernet Korea or CyFam, and also Cybernet Systems Malaysia. On top of that, we also have 3 software developer company, which is located in the USA, Canada, and also Europe. So Cybernet System as an engineering solution provider provide all sorts of solutions to essentially meet our customers' need. Now those solutions include the CAE solutions, AR and VR solutions, big data solutions, IoT solutions, IT solutions, and also engineering service. For CAE solutions, we are mainly focusing on supporting our customer in utilizing CAE in their way of doing businesses. So application areas that we are supporting, including the mechanical solutions, optical solutions, electrical solutions, and so on. So next we move to the introduction to Ansys. Now Ansys has been around for more than 50 years now. Originally started in the USA, in Canonsburg, Pennsylvania to be more specific. Ansys started off providing the user a software or a solutions for finite element analysis, for structural analysis, and then over time Ansys has been growing to becoming this one of, if not the most used, the most popular CAE software out there. Nowadays, Ansys also provide not only for structural solutions, but also fluid solutions, electronic solutions, material solution, embedded software and system solution, and so on. Now that give an opportunity for the user to do a multi-physics analysis as well, which essentially combining several physics together in one analysis. So you can do analysis that include structural analysis and also fluid analysis at the same time, which is essentially one of the strong points of Ansys. Now, due to the fact that Ansys provide a lot of solutions for a lot of customers out there, Ansys now have a global customer numbers of over 45,000 around the world, and also has been used in a wide range of industries. Now that include industry such as the automotive industries, aerospace industries, medical industries, construction, so on and so forth. So as I briefly mentioned previously, Ansys support a lot of physics out there for you to include in your application. Now these are some of the major, I say, product of Ansys, namely mechanical solutions, fluid solutions, electronic solution for designers, and also some additional options on top of that. So mechanical solution, as you can expect, is more focusing on the structural analysis, which can include static or dynamics, impact analysis, thermal analysis, fatigue analysis, topology optimization, and so on. For fluid solutions, on the other hand, you can do something like the general purpose thermal fluid analysis, aerodynamic analysis, rotating mechanical fluid analysis, and so on. On the electronic solution side, you can expect or you can do the analysis something like the S parameter extraction or signal integrity, power integrity, and electromagnetic interference analysis, and so on. Solution for designer is more focusing towards designer instead of CA specialist. This product is essentially more user-friendly and more easy to use. Therefore, it is more suitable for designers who may or may not have any experience on using any CAE product before. So this comes in terms of the product called the Ansys Discovery. Ansys Discovery is specializing in design and also analysis for designers. And then on top of that, some additional options offered by Ansys include the parallel computing module, which essentially allows for a parallel solving. Take advantage the modern CPU that have multi-cores, so you can essentially run your analysis faster. Ansys also offers a material data selection library for you to have a more robust, a more comprehensive material library that can help you to further explore the capabilities of Ansys without having the need to go through or having the need to go through the trouble finding suitable material for your analysis. So next, I would like to introduce a little bit about the Ansys Workbench. Now, before we talk about Ansys Mechanical, Ansys Workbench is actually the first thing that you will see whenever you would like to use the Ansys Mechanical products. So what is Ansys Workbench? Ansys Workbench is essentially the central of which you do your analysis. So it allows for you to centrally manage all of your analysis processes within the same project schematic. So in this case, it allows for a easy to understand analysis process and also easy to understand the method of which you do you configure your analysis by the build and by this drag and drop methodology. So as you can see right here on the screen, we have the setup of a thermal stress analysis. So you do the thermal analysis, and then afterward you do the static structural analysis to evaluate the stresses. So with the Ansys Workbench, you can easily drag and drop this analysis into the project schematic, connecting them together, and then allow you to essentially manage all of your analysis in a more comprehensive and constructive way. With Ansys Workbench, you can also do the multi-physics analysis that I briefly mentioned previously. So it allows you to drag and drop and combine few physics together. In this case, we can see a combination between fluid analysis and also structural analysis. This can be achieved either by using one-way or two-way couplings workflow. In this particular case, we can see that we are evaluating the thermal management systems of a PCB. And then from there, we would like to evaluate also the stresses being developed inside the PCB. So we combine those two physics together to establish a multi-physics simulations workflow. And then this can be done with the Ansys Workbench. So next we move into the Ansys CFD. So what is CFD actually? So CFD in essence is a branch of physics that deals with the study of mechanical fluids. So fluid, in this case, we can say in terms of a liquid, it can be a plasma, it can be a gases, and also in CFD, when we talk about the mechanics of fluids, we are also taking into account the forces acting on this particular fluid as well. So with that, we can evaluate something like in this particular case you see on your screen right now, evaluating the flow pattern around a structure, in this case, particularly a very large structure, which is the Mount Fuji itself. We are evaluating the flow pattern around this Mount Fuji. To do so, CFD analysis are required. So you can evaluate the region where is the strong wind occur. We can also evaluate the vortices or the turbulence that has been going on around this particular mountain, so on and so forth. So CFD allows you to do that. So CFD is actually based on the Navier-Stokes equations that we all probably know. So it describes how pressure, velocity, density, and temperature of a moving fluid are related to one another. So ultimately, with the CFD, you will make use of numerical methods and also some mathematical modeling and software tools, and also the computing hardware to analyze the complex problem that involve any kind of fluid flows. So something like you see on your screen right now, the flow and temperature inside a cafe as well can be evaluated using CFD. So you can include the temperature boundary conditions and also the fluid flow or momentum boundary conditions to evaluate the region that is too hot, region that is too cold, the flow pattern around this interior of a cafe, and so on. So all in all, CFD help you to know the velocity of the fluids, the temperature of the fluids, or the body that the fluids interact with. You can study the concentration of gases in a certain confinement. You can also evaluate performance of a machine, something like in the application that I can think of right now, like in the turbo machinery. You can also evaluate the stresses that has been caused by the fluid. So like something like a stress distribution in a tank during a sloshing event. So CFD can help you to know pretty much anything related to a fluid flow. So when we talk about industry's application for the CFD, so CFD has been used, like I mentioned previously, has been used in all kinds of industries for quite some time now. This is due to the fact that more and more people have access to a capable computing hardware. So nowadays you can just simply go to any shop and then buy a very good computer to do, a CAA analysis. Therefore, plus the requirement of industries nowadays is getting more and more strict, I should say, more and more particular. So you do need tools such as CFD software or application in your design and development. So CFD has been used in the automotive industries for aerodynamics or battery thermal management system. Nowadays we are talking about EV. So battery thermal management system is actually really important. Therefore, CFD has been used in order to evaluate the way to develop the very optimized, very good battery thermal management system. Also has been used in aerospace, again, for aerodynamics or to evaluate the wing flutters. In manufacturing, we've seen CFD has been used in some kind of a chemical reaction between two different components of a fluids, or we are talking about the combustion phenomenon, combustion processes where you can include the chemical composition of each of those fluid and then see the reaction. In healthcare, we saw that CFD has been used in the development of medical ventilator. Some also has been used to evaluate a blood flow inside a blood vessel. Electronics, again, CFD has been used in some kind of a thermal management system of the electronics assembly, mostly on the heat dissipation device like a heat sink and so on. And then for construction, like I showed you just now regarding the analysis inside a cafe regarding the thermal or the HVAC inside a certain construction or inside a certain building, you can include CFD in your analysis as well. So now we move to the Ansys Fluent. So what is Ansys Fluent? So generally speaking, Ansys Fluent is the high-end general purpose fluid analysis software. So with Ansys Fluent, you can expect something like a general thermal fluid analysis and also some other analysis function that is, pretty much synonymous with CFD analysis. But on top of that, Fluent can also provide some of the more complex features or complex solving capabilities, especially when it comes to a analysis that involve a multi-phase flow, reaction or combustions, analysis that involve a rotating machinery or a moving machinery, for example, heat radiation, for example. All of those can be done with Ansys Fluent. So Ansys Fluent in of itself has the ability to cover most of the application out there. So again, Ansys Fluent, because of its capabilities, wide range of capabilities, and also because of its accuracy, Ansys Fluent has been around for quite some time now and has been optimized very well. A lot of engineering resources has been put behind this particular Ansys Fluent solver to further optimize to make it more accurate as time goes by. Therefore, it has been used in a lot of industries out there and also a lot of academic research as well. So again, like I briefly mentioned in the previous slides, there are various simulation types that can be done with Ansys Fluent. You can include any sort of turbulence model in your analysis. You can do thermal fluid analysis. You can include the thermal boundary condition, multi-phase flow, which essentially include the different kind of phases of fluids inside the same domain. Multi-species flow include different species of fluid, different species of gases, for example. Moving deforming mesh, which allows for you to I say, be more economical when it comes to meshing your problems. The mesh will become more adaptive to the region which is require high accuracy. In turbo machinery industries, you can also use Fluent because Fluent is very capable at including the mechanical movement or mechanical rotation of the of your design, and then see how the fluid react around those particular moving object. So these are some of the I say simulation types available inside Ansys Fluent. There are certainly much more than that. We are talking about when it comes to battery thermal management system. You can include the charge and discharge of the battery as an input for you to do battery thermal management system, for example. So there are a lot of Ansys Fluent capabilities. So if you have some kind of analysis that you think of that you would like to do with Ansys Fluent that I did not cover in this webinars, you can let me know in the chat box. So yeah, let's go through some of the features and also type of analysis inside Ansys Fluent. First one here, we have the general fluid analysis capability, the thermal fluids analysis. Essentially, the analysis to evaluate the heat transfer across a system. Inside Ansys Fluent, all heat transfer modes is available to choose from. So that include conduction, convection, and also radiation. So in this particular case, for example, the battery cell cooling, which highlight this feature very excellently, I should say. You have a thermal body, or you have a body that generates a certain amount of heat, and then you would like to see the performance of the fluid flow surrounding it. And then next, turbulence as well, like I mentioned previously, various turbulence model to choose from. And then essentially allow us to identify the flow pattern surrounding a certain body. So yeah, there are various turbulence model to choose from, and also additionally, Ansys Fluent allows for a compressible fluid to be included in your analysis as well. So when we talk about compressible fluid, it is most likely being used in the application of supersonic or hypersonic aircraft or jet, for example, or any other kind of fluids that is, in the operate in a very high velocity. So these are capabilities that Ansys Fluent can cover with the capability of the compressible fluid being included in your analysis. So for example, you can evaluate the contour plot of the Mach number around the wing, or you can evaluate the shock wave by evaluating the density surrounding a moving object, for example, and so on. You can also combine a different type of fluid species or fluid phases in a certain confinement in the same fluid domain as well. So multi-species flow analysis can be done with Ansys Fluent. So this analysis includes a different type of gases, essentially. Say, for example, the concentration distribution during nitrogen purge. So we can evaluate the mass fraction of the oxygen and also the mass fraction of the nitrogen inside this fluid domain. You can also do the multi-phase flow, which again a flow or analysis that include different phases of fluid. Either it is liquid plus gas or liquid plus solid. For example, maybe we are thinking about an application like a nanoparticle inside a cooling fluid, for example. So that is one of the types of multi-phase flow analysis that you can do with Ansys Fluent. Like I mentioned briefly, previously, you can also include chemical reaction between two different fluids and its compositions. So combustion, obviously, one of the, most used capabilities of Ansys Fluent. This analysis, you can identify the changes in mass fraction for each of those components of the fluids when it's reacting with one another. And then from there, you can evaluate the temperature being generated, the velocity of the fluid flow by the combustion, and also the mass fraction after the combustion stage or combustion process has taken place. Reaction, for example, again, pretty much the same concept, the same basic principle as combustion. We see this reaction between two different fluids compositions or fluids types. You can also include thermal conditions and then see how this reaction took place under a different thermal condition. For example, here we have the chemical vapor deposition analysis of the gallium arsenide. So this is mainly used in semiconductor analysis when you would like to, create the substrate, see the reaction between the chemicals. So with combustion or chemical reaction model, there are various to choose from. You can even couple it together with one of the Ansys product called the Chemkin, Ansys Chemkin. Ansys ChemKin is a specialized tool for chemical reaction analysis. So you can even include the ChemKin mechanism import features into the Ansys Fluent to further, I should say, if you are really into the setting up a very specialized chemical reaction module. Next, we have the adaptive mesh capabilities of Ansys. Also, we call it as MDM, or moving deforming mesh. So moving deforming mesh allows you to compensate the change in position of an object within this particular fluid domain. So as you can see in this example here, we have a moving ping pong ball. So it is floating. And then as the ping pong ball moves around, the mesh surrounding that ping pong ball also adapt to become more and more fine around the region of the ping pong ball. So what it does is that it instead of meshing the entire fluid domain using fine mesh, you can choose these particular features allows you to pinpoint exactly essentially the region of which requires a more denser or more finer mesh for more accurate results. So ultimately it helps you to save some time. Like I mentioned briefly previously, you can include geometry movements or some kind of mechanical movements into your fluid analysis as well. Now this is become an advantage in certain application. For example, the stirring tank, in some cases in the manufacturing processes of a medical manufacturing process, for example, where you include different kind of fluids species or fluid phases inside a certain confinement, and then you would like to see the mixture of these fluids when you apply these mixing, the stirring conditions into that particular fluids region of fluid confinement. And then from there, you can evaluate the evenness or the distribution of each of the mass fraction of the composition that you just add. Also, very useful in the turbo machinery application as well, where you can identify something like the velocity and the pressure distribution between the turbine blade, where you can evaluate a phenomenon which is called the cavitation around these fluid blades, around these turbine blades, which can be very risky when it's developed onto the turbine blades. Therefore, with CFD, with Ansys Fluent, you can evaluate this firsthand using these capabilities. So next we move to the application example. So here I would like to show you the gear lubrication analysis. Gear lubrication is one of those IC application that can use a numbers of Ansys Fluent features into the same to solve the same essentially solve the same problems, I should say. So in this case, it combines multiple Ansys Fluent features into the analysis, and therefore gives you a robust and also accurate simulation. So the features that is being used for this particular analysis include the moving deforming mesh, a multi-phase flow, rotational movement, and also thermal fluids or CHT, conjugate heat transfer analysis. So by combining all of these features inside Ansys Fluent, we can evaluate the prediction of the splash pattern inside the casing and also around the gear as well to ensure a proper lubrication. We can also compute the temperature distribution of the lubricant, the gears, and also the casing as well using the thermal fluids analysis capabilities. You can also evaluate the viscous losses inside the fluid as well. So again, this one of those applications which require a lot of functionality from CFD analysis, not only for fluid flows, but something that can help to get a more accurate result, like a moving deforming mesh or the multi-phase flow, for examples. Another features that I would like to highlight when it comes to the Ansys Fluent is that you can include parallel computing in your analysis. So what does it mean? Essentially is that you take advantage of your multi-core CPU. So if your CPU have more than one core, which I should say all modern CPUs now have more than one core, so you can take advantage of those, run your problem parallelly, and then you can essentially speed up your analysis. This case, for examples, we have the number of mesh or number of cells of about 30 million. So traditionally, to solve a 30 million number of cells worth of problems, it will take quite some time. But by leveraging the parallel computing capabilities, by leveraging the CPU's core number on your machine, you can reduce that number down. So for example, we have here we configure the number of core used. So when we use 10 instead of 4, we can reduce the calculation times by about 57%. And then as we go up of the number of core, we can further reduce the time for the calculation. So yeah, Ansys Fluent can include the parallel computing to speed up your analysis. So next, I would like to highlight the feature of Ansys, which is the Fluent Mesh. So Fluent Mesh is natively available inside the Ansys Fluent. So if you purchase the Ansys Fluent, you will get the Fluent Mesh together with your license. So you don't need to rely on any kind of third-party mesher or some sort, because everything is already in there. So meshing is actually very important when it comes to numerical analysis or CAE analysis. Meshing is essentially the core of this kind of analysis. To mesh something appropriately is also very important in terms of getting the accurate results for your analysis, and also taking care of the calculation times. I mean, you can mesh your model with the highest finest mesh available, but then it will take a very long time for you to solve the problem. So finding the right balance is important. And also, when it comes to meshing, it can be a bit overwhelming for the new user to mesh their model. Sometimes when someone don't really have that much of experience in CAE analysis, CFD or FEA, meshing the model can become a little bit overwhelming and can be quite difficult to some extent. This is where Fluent Meshing come into play, I should say, because Fluent Meshing allows for a very simple, very straightforward meshing workflow. So this allows the reduced man hours more than before by advancing the work according to the workflow. You can just follow the workflow from top to bottom. You can get a very good mesh at the end of your meshing processes, because again, the Fluent Mesh knows what is the best for your particular model at that point. So it will give you some kind of like suggestion, I should say, for you to use, and then almost automate the process all the way to the final mesh. And also with Fluent Meshing, you can include parallel processing as well to speed up the meshing process. So there are different kind of meshing available inside the Fluent. You can choose between one or two available. So you have the polyhedral mesh or poly plus hexacore mesh, for example. For highly accurate prediction of a fluid flow, polyhedral is the best one to go with, simply because each of the cell of the polyhedral mesh have a more neighboring cell surrounding it, and therefore allows for a better and more smooth results contours. But if you are trading between accuracy and also performance, you can combine those meshes together, different kind of elements together. So you can maximize the solver performance by reduce the cell count and retain a certain degree of quality by combining the polyhedral and also hexacore mesh together by using this mosaic technology, which is available inside the Fluent. Next, if we are talking about the learnability or the learning curve when it comes to Ansys Fluent Mesh and also Fluent solution, the learning curve is pretty much, it's not really that steep, I should say, because moving from one process to another doesn't change much in terms of GUI, so you don't need to relearn multiple workflow or multiple windows for you to do your work, because everything is pretty much the same. Now this is what I mentioned from of the workflow from top to bottom. So inside Fluent Mesh, you can just follow the workflow from top to bottom. You can first start with the import geometry. You can add local sizing, or you can choose to not add any local sizing, because when it comes to sizing, Fluent knows, or Fluent will suggest a good sizing for your analysis. And then afterwards, you can describe your geometry in more details. Where is the inlet? Where is the outlet? Where is the walls? And then you can add boundary layers as well at the wall to further compensate the separation at the wall. And then finally create the volume mesh, I should say. So just follow the workflow from top to bottom. So here is the typical, I say, Ansys Fluent workflow from start to finish. So first, what you need is the geometry, CAD or CAD data. So CAD data can come in any kind of CAD format. So you can import either in SolidWorks format or CATIA formats or AutoCAD formats and so on. So you can import those into the Ansys environment for start. Then afterward, you move to the meshing. Again, you can use the Fluent Mesh to do your meshing. Just follow the workflow from top to bottom. Really straightforward there. Then afterwards, you move to the Fluent Solutions to do your pre-processing. Now this is where you define all of your boundary condition and also your simulation environment overall. So this is where you define your fluid material properties or fluid properties. You can also define your solid properties if you include solid in your analysis as well. This is where you define your thermal boundary conditions, your velocity at the inlet, the pressure at the outlet, and so on. So all of this is defined during this process. And then afterward, you run the solutions and then you get the results. You can evaluate the result using the post-processing, which is available inside the Fluent as well. So you can do post-processing with Ansys Fluent. There are a lot of capabilities available there. All right, so now let's move to the demonstrations that I've prepared for you. Now this demonstration is going to be done using the Ansys Fluent. And then we are going to go through kind of like step by step from start to finish to essentially give you an idea of what to expect with this particular software, the Ansys Fluent. So yeah, let's move to the demonstration. Okay, so here we are inside the workbench. So here is basically where we start all of our analysis. Whichever analysis that we are planning to do, we can start it here in the workbench. So briefly, I mentioned previously, the workbench is where you centralize all of your analysis together. Same thing with the CFD as well. On the left side of the windows, you can see all of the analysis available for you to choose from. Depending on the license that you have, these options may be varied. And then right here on the right side, we have the properties of each of the cells. And then down here, we have the file directory, essentially. So for this particular analysis, we are going to start with the fluid flow. We can find ourselves here, fluid flow, Fluent with full meshing. So this fluid flow analysis will be done using Fluent. So I simply drag and drop it inside the project schematic. And then we see the options here. So the first one here is where we import geometry, and then we include the meshing, and then all of the setups and solutions will be done using the Fluent. For the geometry import, you can simply right click here on the geometry, and then go to import geometry, and then you can browse to find your CAD file, but I already have it here, exhaust manifold, so I'm just going to click there. Again, for the geometry, you can choose whatever CAD format of the geometry that you would like to use. So now, after we've included the geometry into our analysis, we can move to the next part, which is the meshing. So in order to identify whether the import is successful, you can see that there is a green check mark here. So green check mark indicate that this process has successfully been done. So here we have refresh. Refresh means there needs some update, and then question mark simply means that nothing is defined yet. We are not yet going to go there first. So first, let's go to meshing. So we can simply double click on mesh, and then it will prompt this window. So this window, we can first specify few options here. I would like to use double precision, for a more accurate results. And then down here we can configure how many cores we would like to use for our analysis. In this particular case, for the meshing, I would like to use 4, and then automatically for the solving as well, it will specify 4 cores for you to do analysis. If you have a high-end GPU as well in your machine, you can choose to include your GPU as part of the solving process as well. So you can include it there. Now I finish specifying this part. I can just simply click on start. Okay, so now we are inside the Fluent Mesh GUI or Fluent Mesh windows. So again, at the left side, you can see that the workflow that I mentioned previously, from top to bottom, really easy to get through. We start from the top, from the import geometry. When we click there, everything is already being included here. The directory for our CAD as well is already being included here. I can just simply click on import geometry. And then after a few minutes, you can see that the geometry will be displayed in this graphics window right here. Okay, so now the geometry has already been successfully imported into the Fluent Mesh. So here is how our geometry looks like. So in this case, we have 4 inlet for the manifold from the combustion processes. So we have 4 inlet from the manifold, and then 1 outlet here at the end of our exhaust here. So here the naming of this surface has already been done in the CAD software that I've used. So in your case, if you would like to name your surfaces for inlet or outlet or walls boundary condition, you can do so in your respective CAD software. So I've already done that. So next step is to add local sizing. So in this case, I would not like to add any kind of local sizing, because I suppose it is not necessary for this particular case. So I simply click on update. So here, like I mentioned previously, the Fluent Mesh will automatically generate this number for the minimum and also maximum cell size. So it knows your geometry, and also it will come up with this number as well. So again, if you're not familiar with meshing, you can just simply follow through. Just go with the number that's been provided and then click on generate the surface mesh. So Ansys Fluent Mesh will start by meshing the surface of our geometry first, and then afterwards, at the end, after we've defined some describe our geometry even further, only then it will mesh the entire volume of our geometry. So here is how our surface mesh looks like. So we can see here at a certain region where the mesh is quite fine to compensate the curve and also some of the complex feature of our geometry. And then we continuing on by describing our geometry. So here on the describe geometry, in this case, we can choose between 3 options. So here in this case, we only have the fluid regions. If you only have solid region, you can choose to do so. You can also do analysis by clicking here, select this option. But in this case, I only have the fluid regions with no void, so I'm going to choose that. The third option is when your geometry consists of both fluid regions and also solid regions, then you can select that one. This one change the boundary types from wall to internal. I don't need to do that in this case. For shared topology, again, I don't need to do that because I only have one body here. So I've specified everything I need, and then I click on describe geometry. And then again, all of this name has already been predefined in the CAD software that I use. So it will come up here inside the Fluent Mesh as well. So for the inlet, I have the velocity inlet for number 1, 2, 3, and 4, and then one outlet at the end, and then the rest is going to be the wall of our geometry, of our fluids. And I simply click on update boundaries. And then region, I only have one region, which is the fluid region. If I hover my mouse here, you can see the fluid region there. I click on update regions. And then boundary layers is simply means adding inflations at the end, near the wall of our geometry. So what it does is that it will consider the layered separation at the wall much better than when we didn't include any kind of boundary layers at the wall. So this is recommended to be added in each of your CFD analysis, fluid analysis. So in this case, I will simply click add boundary layers here. And then I go to the generate the volume mesh. Sorry. And then here on the generate the volume mesh, I will left everything as it is. And then I simply click generate the volume mesh, like so. It will take sometimes depending on the complexity of your model. So here we already have our final mesh that's been used. It is a polyhedral mesh, as you can see. And then you can also see some layer of inflation there, which from we add just now. And then we can use this as a capping plane to see the cross section in whichever region that you would like to see. Okay, so the mesh looks just fine for this example. So yeah, that's basically how you do meshing inside the Ansys Fluent. Pretty straightforward. You can just follow through all of the processes here, which is from top to bottom workflow, and then you can get within the region of a very good mesh. In some cases, you do need to add some customization. You do need to put some user input in order to get the mesh that you would like to use for accurate results. But in most cases, I say for a best baseline mesh for the first time you do analysis, you can just follow through this workflow from top to bottom. So now we've done with our mesh, we can move to the solutions. So you can click here, switch to solution. When you do that, you can just simply click yes. And then it will bring us from the mesher to the Fluent solutions. So like I mentioned previously, the GUI looks pretty much the same from mesh to the solution, to the pre-processing. So there is not going to be any, relearn process needed when you move to from one process to another. So here we can go first. I would like to show the mesh, so I can go to display, and then I can click edges and faces. I click all of this region. I choose all of this region, and then here simply click display. It will show where is the inlet and also where is the outlet and also our meshing. I can also use this feature here on the info and then click on size to show us how many cells that we have. In this case, we have just under 100,000 cells, which is, I say, relatively conventional for this simple setup here we have. And then on the left side here is where you do all of your pre-processing and also solving and also post-processing. So everything can be found here on the left side. The same thing also can be found here at the top side by going to different tab here. So depending on your preference, you may use it here or at the top. You can specify everything using the tabs at the top, or you can choose everything on the left side here. Okay. So first, on the general tree here, we can select either to use pressure-based solver or density-based solver. Most of the time, you are going to use pressure-based solver, but when we started to go into some compressible flow problems, compressible flow analysis, we might want to consider to change to density-based. Then down here, we can select between steady state or transient analysis. In this particular case, I'm just going to stick with steady. For gravity, again, I'm not going to include gravity in this analysis for time's sake. So on the model here, we can again configure a lot of things for our analysis. You can start to configure if you are using multi-phase flow. If any kind of thermal analysis involved, you can choose to turn the energy equation on. Here is where I say the important thing is the turbulence model that you would like to use for your analysis. In this case, I'm just going to stick with the default here, the K omega with the SST. And then again, the rest is not necessarily needed for this analysis, this demonstration that I would like to use today. So you can turn on radiation. You can choose you can choose to do a flow with the different species on, and some other thing, battery model. If you are doing any kind of battery thermal management system analysis, you can turn off the battery model. And then down here is where we specify the material. So if you right click here and then click on new, there are several materials that you can choose from here on Fluent database. So you can see there are a lot of other kind of material that you can choose from, all sorts of chemicals or fluids to choose from, gas or liquids and so on. In this case, I'm just going to use air, which is not necessarily the kind of gases you found at the back of an exhaust, but for the sake of demonstration, I'm just going to stick with air for now. If you have your own material, you can change the name here and then specify the properties for your material and then click on change or create here. Simple as that. And then if you have a solid as well in our analysis, we can specify the material for the solid as well. And then down here we have the cell zone condition. This is where we define the material that we'd like to use for our fluids or our solid. So if we have different material that we like to use, we can go here on the cell zone condition and then choose different material that we like to use. And then all sort of other options as well. So mesh motion, the one that I mentioned previously, you can also apply to this particular region or cell zone. If you have some kind of a source term, some heat generation that will be going on for the entire duration of the analysis, you can turn on here. Fixed value, again, same thing, you can switch on here. So a lot of customization. Next, we move to the boundary conditions. Again, boundary condition, there are several boundary conditions to choose from. In this case, for the inlet, we are using velocity. But if you right click here and then go to the type, there are different kind of inlet that you can choose from. Pressure inlet, mass flow inlet, symmetry region, exhaust fan, so on and so forth. So a lot of customization there. So in this case, for the inlet, I would like to specify velocity magnitude of 1 meter per second. Okay, for the first, I hit apply and then close. And then for the inlet 2, slightly less. Let's try 0.85. Hit apply. Inlet 3, again, you can specify any number that we like depending on the application. I'm just going to use 1. And then inlet 4, I'm just going to use 1.2 in this case. Hit apply. Okay, so that is all of our inlet boundary condition has already been applied for our analysis. Internal, in this case, we can just let it as it is, because there are nothing to change about that. On the outlet, again, there are several outlet boundary conditions to choose from: mass flow, pressure, velocity, not velocity, but yeah, pressure, outlet van, mass flow, and so on. In this case, we are just going to use pressure outlet. Here, I'm going to use gauge pressure 0, which same thing as defining, which same as 1 atm, because this is a gauge pressure and not absolute pressure. We specify 0 here. One thing that I would like to highlight is that if you have any kind of thermal boundary condition, say for example in the case of exhaust, you do have thermal boundary condition in the actuality. If so, you can include thermal boundary condition. So essentially on the inlet, you specify the temperature of the fluid at the inlet. Then as for the wall, again, there are several customization, I should say. There are different ways that you can configure your walls. In this case, my wall is stationary. I specify no slip condition for the wall, but if you know a specific shear of your wall, you can do so by changing it here. But in my case, I'm just going to use no slip in this case. So next, what else? Method, yeah. The rest of this is just a more in-depth way for you to configure further your analysis. In this case, like a reference frame, for example, if you are involving something like in turbo machinery application, for example, you do need to specify reference frame for you to specify the rotation and so on of the fluids. But next we go to the method. Now method, we can select different ways for you to choose between the pressure velocity coupling, in this case because it is pressure-based solver. Either use couple or simple. Couple will give you the best coupling between pressure and also velocity. And then you can, discretization of each of these components as well can be specified. So either use second order or first order or standard and so on. So depending on the analysis that you would like to do. In this case, I'm just going to remain as it is. As so, and then I'm going next to do what I'm going to do next is to go to the initialization. So the second last things that you should do before you run the calculation is to initialize everything, set everything to the initial conditions. In most cases, for steady state analysis, you can just use hybrid initialization. For more controllability, you can go to the standard initialization and then specify each of these components here. Maybe in some cases, the initial velocity in X direction, for example, is not 0, depending on the analysis or application that you are doing. So here on hybrid, just go to hybrid initialization and then click on initialize. And then we initialize everything. We'll say that initialization is done. So next we can move to the run calculation. So after we've done our initialization, you can see down here again, hybrid initialization is done. Go to the run calculation tab here. And then here we can specify a few things, most importantly for, in this case, steady state analysis, or to specify the number of iteration. So number of iteration, I should give it a few, maybe 500 in this particular case. Depending on the complexity of your analysis, all of this value can be different. When we are doing transient analysis, we can specify the time step and also the time step size. So depending on how long you want to do your simulation, you can specify on the time step settings and also time step size settings. Okay, so now we have specified number of iteration. We can just simply hit on calculate, and then it will start to do the calculations from here. Now we can monitor these residual graphs here, each of this iteration. So when we reach conversions, we can expect that the graphs will become, flat or stagnant, or reach a certain amount of pattern that we can say that it is convergence. There are a few other ways for you to evaluate whether or not the result is converged. I will show you after we've done this calculation. Okay, so now here it says that calculation is complete, which means that we've already used up all of our iteration that we are specifying initially. You can just simply click OK here, and then we can check whether or not our problems there, our solutions there is actually converge. One way to check is to go to the flux and essentially check between the inlet mass flow rate and also the outlet. So here I have the mass flow rate. I can just simply click on all of the inlet and also the outlet, and then I can click compute, and then you can see the net result here is very, very small. So we can say that our problem there does indeed has converged. Okay, so we can close that. So next, after we've done our calculation, we can move to the post-processing. So there are two ways for us to do the post-processing. We can either use everything that is available inside the Fluent. I mentioned previously that Fluent can also do post-processing. So I'm just going to quickly show you how to. We can go here on the graphics and then click on contour, right click, and then click on new. Say for example, I would like to see the pressure at the wall or at the outside wall of our fluids. So I'm just going to rename it pressure wall, and then here contour off. I can select between different results that I would like to see. Here I would like to see pressure. Under the pressure there are different kind of pressure. I'm just going to stay with the static pressure, and then I'm just going to click here on the wall, okay, where we would like to see the results on, and then I'm just going to deselect global range, just use auto range. Then here I click banded. Then I click on save display, so it will display our pressure at the wall of our exhaust. So we can see that here we have the legend, which can show us the value of the color contour here. So red one means high pressure levels, and then as you go down the spectrum to the blue one, which is the lower side of the pressure. So we can see that the pressure here is slightly high compared to the others, and then at the end the pressure is dropping to the certain level, almost zero here. Then here we have some negative pressure going on there as well at this region right here. Okay, so here you can see that at the end we have the results. So here we can do the post-processing using the CFD post, which is a product specializing in doing post-processing for CFD analysis in the Ansys. So I can just simply double click on the results here, and then down here you can see it says starting CFD post. Okay, so right now we are inside the CFD post. So this is how CFD post looks like. We can display everything if we choose to do so. Walls and also outlet. So this is basically how our fluids looks like. Our fluid region or domain inside the post. But I'm just going to select everything for now. And then what I would like to do here is to another ways that you can do the post-processing is by doing creating a plane, for example. So you can go here in the location, and then you can click here plane. Okay, Now this plane is going to be on ZX direction, ZX plane, and hit apply. Okay, somewhere there. So maybe I would like to evaluate the velocity here, for example. So I've made my plane. Next, I can go to the contour here, click on it, click on OK. All domain, I set to all domain because again we only have one domain. On the location, we can change from the exhaust manifold all the way to the plane that we've just created. This time maybe I would like to see velocity. Then I change the contour to 100 to get even more detailed contour distribution. Apply. So here it will show us the velocity contour inside this region there, on this particular region that we create our plane on. So again, vector as well can be helpful when determining the vector and also the direction of the flow. So as for vector, we can click here on vector, click OK. As for the location, let's just click OK. So now we do get our velocity contours and also the direction of which the vector is flowing. So it can be difficult to see inside the volume, but you can change the factors. You can do some changing here, for example, reduce it down a little bit. Like so, and we can see a little bit the direction of the arrow, which indicates the direction of the fluid flows. You can change the rendering, the symbol. Maybe we can choose arrow, 3D arrow instead. Click apply. Then maybe you can see much more clearly the direction of the flow. Again, another thing, streamline can be really useful as well. Hit apply. So here we'll show the velocity as well. So you can see that the velocity increases in this region simply because the volume there is decreasing. Therefore, due to the fact that this is incompressible flow, we can see that the velocity increasing there. And then with the streamline as well, we can see the region of which the vortice has been generated before it's got out in the outlet. So yeah, that is basically all for the demonstrations. I suppose because we are very limited in terms of time, I can only cover some of the features of Ansys Fluent and also in this case CFD Post as well. But again, there are a lot of other features available. There are a lot of other applications that Ansys Fluent can help to do your analysis, like I mentioned in the presentation. So yeah, that's all for the demonstration. Okay, so that is all for me. Thank you very much for joining in. If you have any questions, again, please write it down on the chat box, and I will try to answer all of your questions. Thank you very much.